Okay, so today I'm going to talk about correlation in simple regression. So this is just with two variables, an x and a y. It gets more complicated than this. This is stuff that you would have probably seen in 2126, and we're going to talk about it in a different way. But it's stuff you've seen before, and then we'll move on to new stuff, multiple regression, starting on Wednesday. Right. All the procedures we've dealt with so far have looked at differences between means. That's what we've been doing. We've been trying to determine is, why is that clock off by so much? Anyway, think of what? Oh, an hour. Okay, they haven't changed the clocks. Anyway, all the procedures we've dealt with have looked at means. So, you know, Z and T tests, all that stuff, analysis of variance. But the thing is, you could also think about this as a relationship between two variables, between the independent variable and the dependent variable. So if the independent variable is predicting and the dependent variable is predicted, well, we could maybe think of them as a relationship between those two. That's certainly, it's not a ridiculous way to look at it, is what I'm saying. So, you know, as retention interval increases, memory decreases. That's a relationship between two variables. It's a totally reasonable way to look at it. We just don't typically think of it that way. With a continuous variable, it's very easy to see. So if we have like a variable that is a continuous, let's say it's like low and high or something like that. You might say, well, yeah, there's a relationship, but you just have two levels, low and high. But let's expand this, and instead of talking about, oh, I don't know, let's think about income and IQ, which the world isn't fair. They are positively correlated. It's just the world isn't fair. Nobody said it was fair. And there you can actually see a pretty good relationship because they're continuous variables, right? Or they're discrete with many, many possible values at least. So if we had a scatter plot here, it's not nearly this tight. I wish it were, because I think I'm smart, so I make more money. That's what I'm saying. But these are just numbers I made up. I did not, there's no way the relationship between IQ and income is this high. It's high though, it's higher than you might expect. It's between 0.5 and 0.6, it's really high. That's like 0.8 something. How did I do that? I put a bunch of numbers into I think that must have been Mac, the numbers program, spreadsheet program, and I said, make me a scatter plot. I didn't care about it too much. But a scatter plot like this, you could maybe try to draw a line in here. Move that guy over. And the scatter plot is a great exploratory data analysis tool, and you should think of it whenever you can. You should do them because they give you a feel for the relationship between your numbers. What we need is a way to standardize the variable relationship, even if we have different units. Okay. So if we have different scales, different units. So the correlation between income and IQ should be the same if we're measuring income in Canadian dollars, euros, or pounds, UK pounds, right? So the relationship should be the same. It shouldn't matter, or the relationship between, well, I don't know, latitude and temperature, right? Of course, the higher your latitude, the lower your temperature in absolute value, right? Shouldn't matter if that's Fahrenheit or Celsius. Shouldn't matter. So we should be able to get something that, and also think about this, we're comparing IQ and relationship between IQ and income here. IQ is measured on an IQ score, whatever, let's say, Wechsler Adult Intelligence Scale, could be. And then your income can be measured in all kinds of different currencies, right? So we want a way to make it so these things are standardized. So the first thing we can do is look at something called covariance. So covariance is the variance two variables share. It's a really good, covariance. So take a look at this. This should look to you a lot like a variance equation, except that instead of x minus x bar squared, so in other words, x minus x bar times x minus x bar, we have x minus x bar times y minus y bar. So now we have both variables together. Right? So really, when you look at this, this is a variance equation. Look at it. What's on top? Sums of squares. What's on the bottom? Degrees of freedom. It's just a variance measure. It's just that it's doing it for two variables together, not just one variable. So this measures, again, the degree to which two variables vary together. You're going to hear me say the degree to which two variables overlap. When I say that, I mean they share the same variance, okay? You should look at that and realize that if these were the same variables, in other words, if we had height in centimeters and height in inches, you get 1. Even better, let's make it height in centimeters and height in centimeters. Then it's clearly just going to be 1, right? We're just going to get, sorry, not 1. It's going to be all the variance that those two things have. So, height would have a variance of, I don't know, 80, I'm just picking up a number. Again, that's what we get here too. In other words, all of it would be shared variance. So that if the deviations of x bar and y bar is just the average score for y, you just put a bar over a variable name, that's the average, the mean for that variable. So if deviations from x bar and y bar go in the same direction, you will get a positive covariance. This is the different thing. This thing can be negative. So while it is a variance estimate, this can be negative, because as one goes up, the other one goes down, you'll get a negative value. And I think hopefully you can see that from this. So if it always is, if the ones that are above the x bar are below the x bar, you're going to get a negative number. Or below the y bar, sorry for the second. So what I'm saying here is that you can have positive or negative covariance. And that positive and negative just talks about, is the line going uphill or downhill? Okay, that's all it means. Positive relationship, negative relationship. Positive is going uphill, negative is going downhill. Okay? So that's all that does. So the sign isn't telling you about the size of the variance. It's simply telling you what direction it goes in. So again, this thing can have a negative value, unlike other variance things that we've looked at. Okay? All right. So, So, covariance is a start. This is going to get us somewhere. This is going to at least tell us what direction the relationship goes in. And we can probably look at the variance and the covariance and go, okay, how much of the variance goes together? We could do that. We want more than this. We want a measure of association. How much are two things associated, right? Obviously, where am I going? I'm going to the Pearson correlation coefficient. That should be, blindingly obvious to everyone in the room. Even me, and I am blind. Geez, I don't know, sorry, it's the end of the term, and the material starts to get really weak. Just saying. So we want a standard score, so we get to that point where, if we measure IQ with the WACE or with the Raven progressive matrices test, we get the same association. If we measure income in euros or in, let's pick an obscure currency. How about, the CFA franc in West Africa. Or is that East Africa? Anybody here from East or West Africa? No. Okay, well, one of the parts of Africa. Anyway, it shouldn't matter. We want to get a standard scale. We should be able to do that. Right, and I've created, as you know, of course, obviously we're going to be able to. So covariance is going to depend on, obviously, the standard deviation of x and the standard deviation of y. It must. It should depend on both. Okay. So we don't want it to depend on that. We want it to be independent of that, the final amount we get. So if it depends on that, we just divide by that. That's what we always do. We want to standardize something. Think about what we did for Z scores. We wanted things in standard deviation units, so we divided by standard deviation. We're doing the same thing here, except we're going to divide by the product of the two standard deviations. So we're going to divide by S sub x times S sub y. Yeah. I hope so, because that's what I just said, so I'm pretty sure I'm right. Right. Questions so far, though? You see where we're going, how we're getting. Okay. Okay. Oops. So what we're going to get is something called the Pearson R, which is the covariance. Yeah, that's good. I did get it right. R equals the covariance of x and y divided by the standard deviation of x times the standard deviation of y. You should look at that formula, and I find it intuitively pleasing, because I know that this says these two things together, and we're dividing by the two things completely themselves. In other words, we're going to get a ratio of shared variance to total variance, which is what a correlation is. Very nice. Very nice. Okay, so it looks this should be not so hard to work with. And I mean, I know you guys have all worked with correlations before. You know of them. You've read articles that have correlation coefficients in them, so I know you're aware of them. So if the absolute value, so it's irrespective of sign. Remember, covariance can be positive, going uphill, negative, going downhill. If the covariance of x and y equals the standard deviation of x times the standard deviation of y, so the absolute value of that, then the absolute value of r equals 1, and you have a perfect relationship. So look at this and think about two variables that are measuring the same thing. So height in centimeters and height in inches. They're measuring literally exactly the same thing, just with different numbers, right? So their covariance should equal their standard deviation times the other, one standard deviation times the other one. Look at this. What's the covariance formula? Let's think about that for a sec. What's the formula for where are some markers? Here we go. Right? So remember, the covariance formula is the sum of x minus x bar times y minus y bar, over n minus 1. Now, if x and y are in essence the same variable, in other words, if we've got height in inches and height in centimeters, or even worse, height in inches and height in inches, literally the same thing, this actually should equal that. You see that? Okay. These two quantities are going to be equivalent if x and y are actually the same variable with just different names. Because we got x minus x bar times y minus y bar. We'll expand this. Right? Expand this out a little bit. So that means that equals x minus x bar, times x minus x bar over n minus 1. Okay, because that's squared. But I said x and y were equivalent. So really, these can be y's. Oh, it's the same as that. Do you see that? Okay. That's really cool, right? I think it's kind of neat. Okay, that's kind of cool. So this is why, in fact, this can never be greater than 1. It can't be. How could the variance two things share be more than the variance of the two things? It can't be. It's impossible. How could the shared variance be more than the variance, the separate variance of the two things? It is literally, think about it for a second, it's impossible. Okay. So this is why we can only get values between 1 and -1 for correlation coefficients. It's mathematically impossible to get a correlation coefficient greater than 1 or less than -1. It cannot happen. If it happens, you did it wrong. It is impossible. Okay? You can't make up a set of numbers that give you a correlation coefficient greater than 1 or less than -1. It is impossible. The only way it can happen is if you do the math by hand and do it wrong, okay? So if you ever get a correlation coefficient somehow that's greater than 1 or less than -1, you did it wrong. There is no other answer. Or you have a really bad statistical package if you did it with software. I did. I don't know how that could happen. So the sign of R only tells us about the direction. Again, going uphill positive, going downhill negative. Because the covariance will have a sign, but S sub x times S sub y will always be a positive number. Always be a positive number. Right? Okay. So the sign of R only shows the direction. Questions so far? Hope that helps a little bit understanding why it can't be greater than 1, as I say here. One of my favorite questions to throw at people is which one has the highest correlation coefficient? You know, or which of the following numbers is the highest correlation? -0.7, +0.4, 1.3. It's -0.7. Because, don't ignore the sign, 1.3 is a mistake. You did it wrong. You ignore that one. Right? Every year, I tell people, I'm not going to do that. When I talk 21-26, I'm not going to do it this class. Every year in 21-26, I tell people, if you see something like that, if it's greater than 1 or less than -1, it's a mistake. It's not a correlation coefficient. It's something else. And every year, someone will, well, that's the highest number. It's not very great answer. Okay. So it has to be between 1 and -1. Okay. And it's only straight lines. This is a bit of a thing that says, oh, only straight lines. Because of the math that's behind this, the way the math works, it needs straight lines. It can't have curves. So if we had I can think of let's think of it. Oh, you know what? I got a good variable that has a curve relationship. What about where's some more markers? I brought more markers. Here we go. Anxiety level and test performance. Okay. If we were to plot up anxiety level and test performance, okay, and we have a performance on here and anxiety here. And I think you all know the Yerkes-Dodson law. You're psychologists. You know you need a little bit of anxiety to do well on something. Just a little. You don't need a lot. And then less later. And in fact, you get it's a really pretty curve. It's so pretty we call it a law. We don't call a lot of things laws in psychology. Weber's law, Vector's power law. We don't use laws very often. That's the Yerkes-Dodson law, and it just says that for a task that you are not an expert at, a moderate level of anxiety is good. Too high and you're freaking out. Too low and you're asleep. You want something in the middle. This isn't true, by the way, for things you're really good at. For things you're really good at, anxiety actually helps you. But most things in our lives we're not really, really good at. We're not experts at. Most things in our lives we're fair to middling at. Think about a school with a test. That's why I use this as an example. So if we collected these data and got these, the correlation coefficient we would get here, which, look at how pretty that is, would be 0. It's 0 because it's not a straight line. So a really pretty thing like the Yerkes-Dodson law, a nice parabola, upside down parabola, or think of something silly, like a freaking circle, you're going to get 0. Okay? Because it's looking for straight lines. The math behind this is looking for straight lines. So that is a constraint on this kind of statistical test or statistical procedure. You have to have a straight line relationship, what's called a linear relationship. Whoops, and that's a bit of a pain. A lot of our stuff is, a lot of the things we deal with in life sciences in general are linear. Not everything is, though. There's a lot of parabolas and a lot of normal curves, and they can't be dealt with here. They can be dealt with other techniques that are similar. Okay. It'd be nice if we could predict y from x. Right? It'd be nice if we could predict y from x. In fact, when you go to a doctor with a new baby, and some of you will have kids at some point in your lives, and you will do the thing where you go, for the first few months, you go every couple of months, and the doctor checks out the kid, and they tell you about the growth, and they'll say things like, for their weight, they're this height, for the, for this height, at first they use length, which is weird, but kids don't stand up at first, so length makes sense. For this length, they should be this weight. And then you'll hear, oh, your child is in the whatever percentile. That's predicting one variable from another. That's exactly what's happening there. I bet you, by the way, that the MD doesn't even know that they're using a very simple statistical technique, because there's no table they look up. It's no big deal. But when you do that, you're predicting y from x. So you're predicting weight from height or length. Right? So, in essence, what you're doing is trying to draw a line through a scatter plot. Okay, so let's just turn that into let's put some points up here, and we'll see what we can do. So I need some points for my line. So there's already some points up there. Let's add some more. And we better change the axes here. The labels, we're just going to call them x and y now. Okay. So I put about 25 points up there. There's kind of a weak, looks like, relationship. As one goes up, the other one goes up. So what we're going to try to do really is draw a line through these points that does a good job predicting y from x. Well, I mean, the first way you could do it is you could just eyeball it. I don't know. There's one. And actually, that's not that bad a line. No, I think maybe it's more like that. Or maybe, no, maybe it's like this. I could make an argument that it was there. Oh, do I want to have it come through the zero? Maybe. They all go in the same direction. I don't think anybody'd agree that we could go the other way, but how the hell am I going to choose which line? Oh, here's a great line. You want to see a line that perfectly predicts all the points? You don't get a lot of degrees of freedom here. I don't know what that equation is, but I predicted the line perfectly. It's useless, but I predicted the line perfectly. Because I have to know every value. I think what I want you to see here is I could make a perfect line, but I have to know all the values in advance, which now means I'm not predicting anything. I'm just reading off a table and drawing a picture. We want some way that works better than any of just eyeballing or just connecting all the dots. Remember when you first, they still do this, they teach you Cartesian coordinates in school, and the first thing they do is they have you get a graph paper and you connect the dots, and then it's a bunny. They still do that? Okay, good. I honestly don't know what happens in school anymore. I'm old, right? So I like to know that some things that I did in school still happen. So we need a way to draw a line through a scatter plot, but to all agree on the line. The most common approach is what's called a least squares regression line. Okay. Is it the best? I don't know. But it's one we all agree on, and we all know the math of how to do it. And that's the important thing. It's, can we all agree on what does this line mean? Okay. So I'm going to show you now a much simpler scatter plot. This one only has 4 lines, or 4 dots. Okay. So the idea here is, and here are 4 dots. One here, one here, one here, one here. It's kind of hard to see them. Is that we have y values, okay? Those are the actual values, the ones you would read off a chart or whatever. And then we have a prediction in our line. Our predicted line is called y hat. Why it's not called y circumflex, I don't know. I think it's because a lot of people can't say circumflex or can't remember the word. So we call it y hat. I love the idea that perhaps in French it's called y avec un chapeau instead of circumflex. I really kind of hope that. But I asked a buddy of mine, and they just say, oftentimes he said to me, I'll just do y hat. So sometimes he says y hat. So look at this. What we have here is we have a line. By the way, again, the line is not the data. The line is the prediction. It's our guess. Well, it's not a guess, it's a prediction because we're trying to minimize these distances. These are mistakes. These vertical lines are mistakes. They're prediction errors. This is wrong. It's not here, it's here. What we're trying to do is minimize the sum of y minus y hat. We're going to minimize that sum. Now, again, I'm not going to go into how this is done, but I think you guys probably all remember, maybe in high school, doing maximum and minimum problems. Remember doing maximum and minimum problems? Because that's all this is. It's what's the minimum? I mean, you probably remember doing local minima and, overall. It's really not, it's something you probably did about when you were 14 or 15 years old. Like, it's not hard math, and we don't even have to worry about it. The beauty of this is we don't even have to worry. Because some people figured it out for us, right? But what I'm saying is, the solution to this is not something that even, your math skills that you had in high school, you could have done this. So it's not scary, okay? All we're doing is making these prediction errors. These are errors, eh? Y minus y hat, that's a mistake. Let's make the total mistake amount as small as possible. Right? And we're going to square it because what's going to happen if it's 0, or what's going to happen is the positive negative thing, it always happens with when we're looking at deviations, so we square it. So what you end up with is a prediction equation. Y hat equals a plus bx. The predicted y equals the intercept. This is where x equals 0. That's where it hits the y-axis. Plus the slope times whatever x value you get. Now, you might say to yourself, when I was in school, we learned it as y equals mx plus b. I know. You're no longer in elementary school. I don't know why they do that. I honestly don't. It's like, that's not how it's done past. Anyway, the important point is, this is an equation. We can plug a number in. And in fact, again, this is what your doctor does when you bring your baby in and they say, they type in the number of centimeters and it says how many kilograms your kid should weigh. It's very straightforward. And that's exactly what this is here. When you think about how salaries are, my salary is calculated like this, in essence. Yeah, there's a floor value. That's the intercept. So there's a floor value for my rank. Okay, my rank is for professor, so it's all fully available. You can look it up if you want. Why you would want to, I don't know. Go read by collective agreement, you can. The end, there's a chart, and it shows our salaries. Not with our names, that would be weird. But it does show, so you could look, for example, so I'm full professor. You look in the full professor chart, and it says floor, that's the intercept, plus some number times x. I forget what the x is. I'm going to make up a number, and I don't think it is this, but let's say it's $5,000 a year. So what happens is it says, here's the intercept, is whatever, and then we take the number of years times 5, and there's Dave's salary. Okay? So it's really straightforward and simple. The difference is, of course, when they're figuring out my salary, hopefully they don't make any mistakes. There's no prediction errors. Hopefully it's always correct. When we're doing this kind of thing, there's going to be prediction error. Okay? So the problem is it's very tempting when you see an equation to go, it's math, so it's science, it must be right. And you got to be careful with that. It's incredibly tempting when you see an equation to worship at the god, the altar of math, and it's not necessarily the right move. So, if you want to find B and A, B is the slope, A is the intercept, you find these actually, B is the covariance of x and y divided by the variance for x. And A equals y hat minus B times, equals y bar minus B times x bar. So these are actually pretty easy to calculate once you have the covariance. Right? So if you have the sum of squares, this is actually not that hard to do by hand. I'm not saying I'm never going to ask you to do by hand, okay? Don't worry. But it's something that one could do by hand, like with like that pair of 20 numbers or something. That wouldn't be that hard. There's a lot of places to make a mistake, is all. But but mathematically, it's not a hard nut to crack. It's doable. Okay. Okay. So. There it is. All right. So A is the intercept, as I said, and that's where x equals 0. It's not necessarily a meaningful value. Again, it's incredibly tempting because it comes from the equation. You think of it as meaningful. But I don't know. If you were doing whatever it is for the weight and height, so if you put in 0, does that help you at all? Oh, so babies that aren't alive yet weigh this? What does that mean? Right? So it's not always useful. Sometimes it is, if the 0 point of x is actually a useful quantity. So the 0 point of x, so for example, again, going back to calculating people's salaries, there are people who have 0 years of experience at their rank, and they get the floor. So that makes some sense, but again, that's sort of more of an analogy. Something like weight and height. You look at that and go, so this is what you should, how tall you should be if you weigh nothing, or this is how much you should weigh if you only live in one dimension and have no height. Because it's not possible, right? So it's not a meaningful value. It looks meaningful because it's an equation. And you also only have to deal with linear relationships. And this is a pain because there are a lot of things in our lives that are not linear. Okay? So if we think about something like height and weight of a growing child, that probably is linear. That probably is linear. As one goes up, the other one goes up, and it's probably a constant rate, and that's fine. But there's a lot of things in our lives that aren't linear. Right? As we found out during the pandemic, a lot of things are actually exponential, for example. So you have to be kind of careful with this stuff. But it is incredibly useful, and these are very powerful techniques, but you have to satisfy their assumptions, and one of them, of course, is the linear relationships. One of the things you should do is look at residuals. Residuals are also called E for error. That's y minus y hat. They're prediction errors. The covariance between the x values and the residuals should be 0. What that means is there should be no relationship between, I'll draw you a picture here, but there should be no relationship between the x values and how big the prediction errors are. So if this is what's called a residual plot. This is what it looks like. You can get one in SPSS when you play with the residual, with the regression and correlation procedures. So this is the x value here, and these are along the y-axis is the e's. It should look like this. They should be equally and randomly distributed around 0. You shouldn't be able to know how big the prediction error is if you know the x value. They should have no relationship whatsoever. So, while it's pretty easy right now because we're talking about one variable, we can talk about more than one variable. we're going to want to look at, residual plots. And we look at these. If you saw this, you'd go, okay, that's good. It's probably it's a linear relationship. But if you saw something where, it underpredicts, then it overpredicts, then it underpredicts, that's probably a curve. If you saw that the prediction errors got bigger as the x value got bigger, that's bad because you're able then to predict how big the prediction errors are. And you shouldn't be able to do that. One of the assumptions is those prediction errors are in fact unrelated to each other. They're independent of each other. Right? If that happens, well, you can't use this kind of statistical technique. The other thing that is tempting, and that's again because we have an equation. And when we see equations, we immediately think, or often think, oh, that's got some exactitude to it that we don't normally get. It's numbers, so I can just plug numbers in. Right? So, if I was predicting, well, like we can do height from weight again. Oh, so you're saying that if someone was 19 meters tall, no, that's not, people aren't that tall. That's not a thing. Or I can think of examples. One of the things that, one of the data set I used to use for when I used to have an assignment about regression and correlation, I got rid of that, was this data set about smoking. And I'll talk more about that when we talk about multiple regression. But I had a smoking data set, and basically a person I know collected a whole bunch of data about 40 years ago or so at the Ontario Science Centre in Toronto, and it was a way trying to figure out how do you get people, like how can we measure how much people smoke without drawing blood or without getting a saliva sample? Because people are really bad at predicting how many cigarettes they smoke. Smokers underestimate constantly. So what you want is you want something where I can ask you 4 or 5 questions, and then I know that I can make a good prediction. And then they also did a physiological measure so they can correlate. Anyway, you can come up with something and see that, for example, if you just wanted to predict how many cigarettes people smoke per day by the year they started smoking, that was actually 2 things that were, of course, as you would imagine, correlated. So not how many years they've been smoking, but what year they started smoking, like how old were they? And it had an x value that had an intercept, meaning that if you looked at the line and drew it past the the youngest person in that data set started smoking was the age, I think it was 4, which is disturbing. But you couldn't go beyond that. But the line did, so you could look and go, okay, so how much do 1-year-olds smoke then? No, you can't do that. Or, oh, how much do people who are 150 years old smoke? Well, none, because they're all dead. And much before 150 if they smoke. So the point is, it's incredibly tempting with an equation. You look and you say, ooh, exactitude. This plus this times this equals the thing I'm interested in. Oh, if that's the case, then I'm just doing that. And the problem is you can't just do that. Okay, so it's something to pay attention to. Don't go outside the range of where you've collected your data from, and it'll be a lot safer. All right, questions about this before we do some review stuff for the final exam, because I got some questions we can play with. Okay, so why don't I stop